All right, welcome back. We are Game 3001 in the winter 2022 semester at George Brown, and it's week 9, part 1 of our broadcast and recording, which is the lecture portion. Let's talk about a couple things. Last time we were around together, and this is before the break, we were talking about pathfinding. Pathfinding was the last kind of section or module that we had on movement, right? We've been talking about movement in the first half. First half is all around, moving, steering behaviors, those kind of things for autonomous agents or AI agents, whatever you want to call them, autonomous characters. And so we talked about a couple of different kinds of pathfinding techniques. One of them was A-star. The other one was a Dijkstra's algorithm. And we also discussed different variants and those kind of things, heuristics. We talked about what those things are. And then in lab 5, the last lab that we did, it was there to support your assignment 2. Now, again, as we've been marking, all of assignment 1 has been marked. All of the labs to date are all up to date. Alex and I kind of sat together in a marking session last week where we pretty much marked everything that hadn't been marked except for parts of assignment 2. We haven't got to all of it yet. We will. And because assignment 2 is more involved than assignment 1, but we found a couple of things that were missing, and I wanted to relate this to you, from the get-go. One of the things is most groups that we were kind of looking through for assignment 2 did not use a full A-star pathfinding algorithm. The call for assignment 2 was for you to find all paths, not just the shortest path. Okay, the shortest path was only one part of the entire algorithm. And that's where people lost the majority of their marks. They just did not. They stopped at one path, or their algorithm would work and then it would get locked up, and as an example, or wouldn't be able to continue. That is not a solution, guys. The solution is for you to find all viable paths. Remember that the kind of the way that the pathfinding would work, right? We saw that it had a different fill pattern, right, from a Dijkstra perspective. Even A-star filled up a lot more of the of the game world than, as an example, the single path we've defined. What we created for you guys, myself and Alex, was a very simplistic structure or a division scheme for pathfinding, which was using a tile-based grid. Okay, that's what it was. And the tile-based grids give you some information or inform your agent on what the shortest path is. But what if the agent can't find the shortest path? What happens then? What happens if it gets blocked, as an example? And with our current algorithm, it'll just, the one we gave you was just one part of A-star. Some people just use the exact algorithm when they built their assignment 2. Guys, when we give you an assignment, you got to take it further than just the labs. The labs are just there to help you move forward. We try and give you as much as we can to get you going. And for the most part, you guys have done very well in incorporating the stuff we've given you. But when we ask you to do full A-star, which was included inside of the pseudocode was included inside of the PowerPoints, I showed you a diagram of how it would fill and so on. That is what you were expected to do. So somehow there was a confusion between that. And no one actually asked the question, should we find all viable paths? Which is exactly inside of your stuff. Let's take a look at what I'm talking about here, right? So, and I'm talking about this first because I don't want people to be upset, when they get their mark back and then they're like, wait a minute, I didn't get full marks for this. Well, why not? We did everything that Tom asked and what Alex asked for, right? But actually, most of you did not, okay? And some people just didn't do it because they're like, well, it's not worth it. I'm sure they did that because, it's going to take too much more time than I have, that kind of stuff. So I'm not doing it, and I get it, right? But at the end of the day, right, let's take a look at the requirements here. So again, you get your place scene and everything else. And this is the wrong one. Let's take a look at the actual one. How about that? This is A2. Simon says, wasn't from lack of trying. Everything I tried didn't work. Okay, but we'll talk about it, what we could have done to take it further. Okay, so, and that's the learning part of it. Okay, so see, here's your placing. So you must include the tile class. We talked about the grid of tiles. Each tile in your map should have a cost value. We did that as well. appropriate actor sprite. Some people use the exact same stuff we gave you. An appropriate actor sprite is not one of the things we've given you guys. You need to use your own sprites. I've said this before. Also, some people did not use the look where you're going algorithm. So they didn't look, we literally just lifted the algorithm right off of the lab and included it in the assignment. That's not enough. There's some stuff that's missing that you got to do on your own. We can't give you everything. Otherwise, there's no evaluation. We're not evaluating you based on the fact that you can, smash together the lab to make your assignment. You got to take it further than that. All right. So interesting map. People didn't know what this was, and they literally had a white screen with nothing on it. That's not an interesting map, guys. An interesting map means some kind of tile set, and some people did do that, and they were very nice. Also, things like sound effects and those kind of things. That was also missing from many things we've seen already, which is pretty bad, right? Because that's easy to incorporate. Super easy. That's like easy marks to lose, put it that way. So that's kind of the scene. And as we go through, it says, using pathfinding heuristic of your choice, Manhattan or Euclidean, you could have chosen either. We recommended Manhattan because of the nature of the movement. Some people also ignored the fact that you can only move in 4 directions. That's what we told you. You can only move in 4 directions. Some people moved in diagonal directions, which is not something that was covered, right? And we ask you to enable the A-star algorithm that you will create to calculate the tile cost from the goal tile outwards, and keeping track of the cost so far, and so on, and just going down to the the shortest path. What you're destined to find is all paths, not just one path. So a couple things that were there, that you guys missed. Some people added, actual keys. Some people used IMGUI. IMGUI was fine. I don't think we docked you for using IMGUI, and those kind of things. But for the most part, it's all possible paths, right? Not just the shortest path. Okay, so please read carefully when you look at this, and especially when it comes down to the requirements at the bottom, right? As an example, when it comes to heuristic mapping and so on, right? And pathfinding, right? So one of the problems that we have when it comes to tracking is what happens when you get into those really weird spots, right? So I'm going to kind of review this a little bit first before we move on, and then we'll get into that. So what I meant by this is, if we look at the grid system, we talked about this in lab. If I have my goal tile and there's some weird, tiles in the middle, some kind of impassable tiles in the middle, as an example, and you get into these weird cases where there's only one way of getting into your, now you designed the map, remember, this is something that you've done as well. So let's look at some impassable tiles. Let's suppose we have an impassable tile set that looks like this. Okay, and which is, I saw one implementation of this, where you have some kind of mountains, or you had a wall or something. And again, impassable tiles, I usually mark with a block just to give you, some idea of what this looks like. Some people also had a river or something that they wanted to cross with a bit of a thing like this. So let's say, for example, these were all impassable tiles because these were all, this is the river, and we have this place right here, which is a bridge, and there's one bridge right here, right? And there's a way of getting to the goal here, and there's ways of, only one way of getting to the goal here. Okay, you're never going to make it. You're never going to get through this, all right? A lot of times. Why is that? Because what's going to happen is, if you use Manhattan, and if you're using the 4 tiles, which is top, right, bottom, and left, right? So just like give you this idea, I'm going to start with the top. Okay, top is obviously farther away than right, so we're going to go to the right. And we're going to keep going to the right, guys. Watch. When we go to the right, we're going to mark all these tiles as closed. Look, this is what's happening with our algorithm. Okay, these are closed, closed, closed. Take a look at this for a second. All right, if we're going to mark this. And this is something you could have used the grid for, the stuff that we've given you already, right? So I went to this place, we went to this place, and we've got all these tiles are closed. Watch. So this is open, 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 right? This is what your thing is going to do, because it's getting closer and closer to this part right here, right? And again, if you look at the diagonal, right, the diagonal hits you something like right here, all right? So once it comes to this point, these 2 tiles, this one and this one, are equally weighted, but because of the way we're doing our right winding, it's going to go this way, okay? And once it goes this way, it's going to come to this point right here. Okay, cool. And now it goes to a block. Okay, it goes to a block. And when it comes to this point, it hasn't marked these ones as closed yet. Okay, but what it's going to do, all right, as an example, let's take a look at this situation, right? What is it going to do? Well, there's no place to go forward. It's more expensive to go up than go down. So it's going to go do something like this. It's going to close this one, and this is going to be its path here. And then it's going to go, when it goes here, this is already closed. And when it goes here, right, now what can we do? Right? Well, we can't go back up because open is not a possibility. And what we want to do is have you go back this way. Okay, back this way. But actually what happens is you get stuck. Why would you get stuck? Even though this one hasn't been closed. Why would you get stuck in this case? What do you think? Sometimes people get stuck right here. Well, here's the thing, right? If you didn't adjust for the algorithm, right, then when you're here at this particular place, this is an open tile, right? Now you're checking the top. Top's not viable because it's in the open list. Checking the right's not viable because it's impassable. You're checking the bottom's not viable because it's impassable. So the only choice you have is to go this way. Okay, let's move one this way. Well, now we're in the same spot. We're in the same spot, right? Because we want to go this way, but we can't go up. We can't go this way. This is what you want the algorithm to do. You want it to go this way and then go across this way, but it doesn't happen, guys. You don't go to this spot right here. You never do it. You get stuck here. And there's a reason for this in our algorithm. All right, so what you're supposed to do is if you get stuck here or something else, and by the way, this is not exactly what it was, right, as an example, because this is good. This is a good case. If it was something like this, you probably could find your way out of here this way. If your goal, if your start was here and then your goal was here. Okay, but what if, just putting it out there, what if this wasn't the case, right? What if it was actually like this? So let's move these tiles just down one more. So this way you probably would find a way out, but maybe not this way. So let's mark these tiles as not impassable. Just showing you this for a second so you understand what the problem is, okay? So you go down to this spot right here, right, as an example. In the first case, you might have been able to find the way out, okay? But in this case, because you've got a way of going down and you have other tiles here that are not marked as closed, you come to this place right here and then you go, okay, so I've already marked this as closed, so I can't go back up there, right, because you're marking down. I'm going to go here, right? So, and then I'm going to go to this spot right here. Okay, when I go to that spot right there, where am I going to go? Well, I can't go back because back is more expensive than going up. Back and up might be either similarly expensive or up might be less expensive in this case. You're going to go up. And when you go up, you're going to mark this as closed. That's what's going to happen. So you're going to go up here to this place, right? As an example, this pot right here. And the only place you can go is this way. And again, you should track what's happening with your troubleshooting. So you can't go this way. This is closed. You can't go this way. You can't go this way. The only place you can go is this way. And you're going to do that. You're going to go here, right? And you're going to keep on marking your tiles as closed. So you're here. This tile and this tile are no good. You're going to go to this tile, right, as an example. And you notice that at this particular place, there's two places you can go, here or here. And guess what? This is more expensive, so you're going to mark this as closed. You're going to go down to here, but this is marked as closed. You can't go through this area here. So guess what you're going to do? You're going to keep going this way. And you're going to keep marching this way, right, around to this spot until you get to the point where there's no place you can go that is not closed, right? Okay, you're here in this spot right here, and now you're going to go up. That's closed. This is closed, right? This is open, and this is closed. Why? Because this is where we started, guys. And that's where you're going to stop. Does that make sense? Does this conundrum, this issue, make sense? You're going to get stuck in this scenario, right? So what do you do? How do you get out of this thing when it comes to pathfinding, right? Well, you come to the point where if you don't find a path in this particular case, you need to have an algorithm that backtracks or keeps track of any branching that goes on, okay? So for example, when I came to each of these spots, remember, each of these spots had multiple directions that it could have gone in, right? Multiple directions. Now it failed here, so we're going to go back to the previous, if you turn somewhere, that's another way of doing it. If you turn anywhere, once you make a change of direction, you could decide, as an example, that is this a branch that I could have gone anywhere? Well, no, I couldn't have gone here. I couldn't have gone here. So this is not a viable place to stop. Let's go back over here. So this is another place that is a kind of a turn, if you will. Okay, I was here. Could I have turned up? Well, this was closed, so I couldn't have gone anywhere. So this isn't a viable path up here. We're just going to keep on going back, right? Because this was closed from before. You're going to keep going here and here. Can I have turned differently down here, right? Well, no, because this was turned, this was closed, as an example, and this was closed. The only way I could have gone was this way. So we keep on backtracking until we get to something that looks like this, right? At this particular spot here. We chose to go down, right? And we closed this choice. We made that choice to close. So the other thing you could have done is backtrack all the way to here, right? This is a one choice. And you could have gone up this way, right? So instead of making the choice to go down, right, you could have chose to go this way because, well, that's closed. And instead of closing this one, we open it. We go this way. That's the way you could have done. Now from here, you would have said, okay, well, that's, closed. That's closed. We're going to go this way. And then you would have found a way out. Okay. But you have to backtrack. You'd have to have your algorithm backtrack again, where going this way, as an example, just has there's no possible way of finding a way out this way, okay? So you try this way. This would be the second path, all right, that you would try. And by the way, this is perhaps not the shortest path. Look at this one. You want to try and go this way down here, right? So again, you could keep trying, recursing back until you find a way of where, if there's another path that comes from this place. We chose only one, we made only one decision, right? Yeah, we made only one decision every single time. We only chose, if we were here, we only chose to go this way, but we could have chose to go this way, or this way. Those other decisions also need to be explored, guys, right? And if you backtrack enough, you'll probably go to this position right here, right? So this way is a way, because you would do something like this. It would be like, okay, I'm here. What's cheaper? Well, I'm probably going to go here. With Manhattan, you're going to go to this spot and then recurse down, right? So this is the way you're going to go until you're going to get to your goal, right? And if we count the total distance, this is one possible path. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 total tile cost, right? What about going down this way? So if I went this way, and that's another viable path, right? Instead of going, this is another possible tile, you're going to go here, and then you're going to march across this way, right? You're going to march across this way all the way to there, right? That's another way of getting there. Remember, we talked about this. Is this way shorter than this way? Probably. Let's take a look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. It's not 22. So by one less or whatever, equivalent, right? Or it's the same. And those are the two viable paths that you're going to find. Once you find a viable path, right, as an example, you need to kind of decide, are there other ones? And you would have to explore every one of them. That is one thing we ask you to do. It's a recursive algorithm that would basically go, okay, well, what if we went this way? Well, what if we went this way? Let's wipe this out again and try it again. What if we went this way? And you'd have basically a bunch of different paths that you would record. We gave you one path, but you would record a bunch of paths. If your shortest path algorithm recorded nothing, if it stopped and there was no place for it to go anymore, right, then you'd have to go back to the last choice, the previous choice, and try it from there. Is there another way of getting there? If I went to the previous choice, right? Okay, cool. And I go to the previous choice and the previous choice and the previous choice and keep going back as much as you can. Christian says, but isn't that basically randomly checking each with brute force? No, you're going to check it based on your path lengths, right? You want to try and go with the shortest possible path. And in some cases, remember we talked about this, Dijkstra's algorithm and A-star algorithm is just as bad, right? Depending on the situation, depending on this case that you've given it this case, right? In an open world example, this wouldn't be an issue, right? Because it would just do the thing it's supposed to do. It'd find the shortest path, right? But we asked you to create obstacles, right, in your assignment 2. And when we did that, when you did your obstacles, some people decided to make a very interesting map that was unattainable. You couldn't make it. It would stop. Okay? Especially since we asked you to allow us to right-click anywhere we wanted and assign a goal. So if your goal was here, right, sure, your thing worked. Everything worked fine, right? But as soon as I move the goal over here, you made this, right? We're going to test it. As soon as I move the goal over here, as a good example, right, then it's going to not work. It's going to fail completely. Your pathfinding algorithm won't find a path. And that is what we checked. Okay. Questions around this idea? Simon says, is this why NPCs tend to cause lag in games? Sometimes. But a lot of times, Simon, the pathfinding algorithm is curtailed, if you will. If it can't find a path, it might say something like, I don't know how to get there. And a good example of that is if you play something like Fallout, any one of the Fallout games, Fallout 4 is an example, and if you direct one of your NPCs to go somewhere it doesn't know how to go, it's going to say, I don't know how to get there, right? So that's something that you can do, right? You can say, okay, fine, I just don't know, I don't have a path for that, right? And one of the things we showed you, what we talked about, was how to kind of show us all the possible paths and how you would do that. All right, so the reason why I bring this up is because some of you may be disappointed with some of the marks because you're like, wait, I did what they said. No, you didn't. You didn't do what we said. We said find all possible paths, right? So please don't get upset when you see it. You're going to get a reduction, and that's where the reduction is going to come from, based on the fact that you didn't, you only did one part of A star, not the full A star algorithm, which finds all possible paths. Okay. Now, again, if all the possible paths it finds are longer, right? As an example, it's going to choose the shortest path if the other paths are longer, but it's still going to explore all the spaces, not just one space. But if you notice the fill pattern, it's going to fill all these spaces from, the start to the goal. Okay. Lucas says, it's impossible to reach. I'm not a magician. Okay, well, it's not impossible to reach. And you don't need to be a magician. You just need to, take a look at the algorithm that was given. And there's other examples online you could have looked at as well, right? To give you a better chance to, sorry. Yeah, it's impossible to reach. I'm not a magician, Yes, thanks. Sorry about that. Yes, of course. I'm sorry, Lucas. But yeah, but at the end of the day, that's what I want you guys to think about, right? How to do that from A to Z. Sorry. That totally like it went over my head. All right. Questions around this, because again, I want to move on. I wanted to talk about this because A2 is an issue, right, with some of you guys, right? Other things we saw when we were marking, guys, okay? Other things we saw for A1 and for A2, some people just did not give a proper video. If you didn't supply a video, your mark 0. If you didn't supply all the proper stuff that we need, you might have got a 0 for that. If your video was unclear, we couldn't see your video, or it was unopenable, inaccessible, you got 0. Or if it was something like, your video was, you couldn't hear anything, there was no sound, you got 0, right? No sound, can't access it, doesn't work properly. Guys, what did I ask you guys to do? Please check your videos. You're submitting your project for you and your partner, and in this case, going forward for assignment 3 and 4, for you and your partners. You're kind of creating this thing for you guys, right? You need to check it. Check your submission. Make sure that I can see it. Make sure that you can see it. Maybe make sure that you can hear yourself. Some people, supplied a video where they have multiple monitors, as a good example. It wasn't just one person, and they were in their video. They were showing the wrong monitor the entire time, right? So, again, these things are things you need to check. This is not a small submission mistake. How do we check your stuff, AD? And this is a mandatory requirement. If you don't understand that, we can talk offline. But at the end of the day, this is not a small thing. This is a big thing. We can't see you. We're not in the same class as you, and we've never met. All right, so we need to guarantee and we need to treat everybody the exact same way. And that's why we've got video requirements. We've had video requirements from the very beginning. This is nothing new. It's not about losing marks. It's about you have not submitted things correctly, right? And we don't know that this, we have to make sure that this is you. Sometimes there's no video at all. So we don't know who submitted this thing. Was it you? Was it somebody else? Did you pay for this to be done? How is it to be done? We can't guarantee it. So from an academic integrity perspective, we ask you to make videos and we have to be fair. Everyone has to be treated the exact same way, and that's why. Absolutely, Rakib, if we have time. Okay. Not everyone. No, there's still some people that are not marked. Okay. All right. Now, the other thing that I wanted to talk about was what about for those people that, had everything in mind, but the video was missing? Now, Alex and I are working it out so there could be a resubmission from the video. If your video was broken, let's suppose, it's inaccessible. Not if the video wasn't made. If your video is just being made now, you're not going to get marks for your stuff. You just didn't submit a video, right? But if your video was working and it was inaccessible because you had made it private instead of public, or something like that, I will allow you, right, to resubmit. Right, I will allow you to resubmit with a penalty. So better than zero, okay? So, and Alex and I were working out some other details. So we'll more on this because it wasn't just one set of groups. It was a bunch of times from different people. And so to be fair, right, like going back to what you're asking, Aiden, right, we don't want to be draconic. It's a lot of marks, right, for this one, 15%. So, we want to give a chance for people to resubmit with a penalty. Okay, so that's the thing. So I'm going to, for the people who had submitted their stuff and there was a submission failure. Okay, so for example, you just didn't hand in a video or, whatever. If you submitted something that was with a video, you had everything and your submission was terrible, there's no, recourse for this. You submitted something that was terrible. Okay. But if you submitted something that, it just is missing, like this video, the mandatory requirements as an example, Alex and I are going to come up with a system where you can resubmit with a penalty, okay? Because we want you to give, we don't want to, especially since this is a lot of marks, we don't want to make it so that, it kills everybody. That's not the exercise, okay? We want to basically try and evaluate you as best and fairly as possible. Okay, so that is on A1 and A2. Again, some things were for both A1 and A2. Both times, A1 and A2, assignment 1 and assignment 2, you did it both times. So it's a systemic issue, right? Something that you either don't realize is required or whatever, But if you haven't made a video for those things, knowing that we are making videos for every lab, we've been asking you to make videos for pretty much everything since you've been at George Brown, for the most part. I don't think it's a requirement that is out of this world. All right, something that we haven't asked you for. Yes, Jack's asking for assignment 3, and this is what we're going to talk about right now. For assignment 3, one of the things that was asked is for you to sign up for groups, right? For A3 groups for assignment 3, and there's also A4 groups for assignment 4. So why do we do this? What if you and your group members don't like each other? Right? You and your group member, and you didn't work well, or they didn't work out, or whatever. Now's the chance, yet again, to find additional members, other people that you want to work with. Now, keep in mind for assignment 3 and 4 that the group limits have increased again to 3. Okay, so now it's 3 people. Why? There's a lot of stuff to take care of in assignment 3 and 4, right? Which we're going to kind of go over again at the end of this lecture. Okay, because I want you guys to have a cleaner idea of what you're required to do. Can you group up with people from other blocks? Yeah, it doesn't matter to me. Doesn't matter to me, right? It's because it's one big, course. That's always been the opportunity. You didn't have to stay within your own blocks for your assignments because Alex and I are marking the assignments together, right? So sometimes, by the way, guys, people send me a note saying, I don't know why I got 0 on this. Check the rubric. A lot of times the answer's in the rubric. And sometimes they said, I don't get why I got 0, as an example, and I didn't mark it. It was Alex that marked it as well. So I'm going to try and answer your question. Bear with me. I did get your email. Okay, I just haven't had a chance to go through all of them. There's a lot that say something like, I don't know why I got this mark. First, check your rubric. The rubric is available to you for each of the assignments. The rubric basically is when you mark the assignment, there's a set of criteria similar to what it looks like for the lab report that basically is a check mark that you did something or you didn't do something. All right, so that rubric tells you where you lost your marks. It'll be, if you got 0 for that one part, it'll show you where you got the 0. Okay. All right, so so this week we're talking about decision making. I'm going to the lecture now, and we'll talk about assignment 3 after this. And for people who want to stick around afterwards for their submission, we can go over. Now, if I haven't marked it, guys, if for example, Rakib, if your submission hasn't been marked, I'm not going to mark it right now live. It's going to be marked in the proper time. It takes time to mark these ones. It's going to be marked in a proper time, the word Alex and I are going to use again to make sure that we're on the same page. Alex and I mark them together for a couple of reasons. One of the reasons we do it is because we want to be consistent. All right. So a good example of that is if I marked everything on my own without Alex and Alex marked everything on his own, our opinions could be a little bit different. And that could cause people to say something like, well, I got something like this from this professor, but the other professor gave me a mark. I don't understand. And we don't want that. So that's why we've been marking those things together. All right, so let's get back to this part, this kind of stuff here. So again, just as a reminder, things that are due, Lab 6, again, is due week 10. So that is not this Sunday, but next Sunday. And I want to just peek into that again just for a second. So if you go to the labs kind of tab inside of your Blackboard, you're going to see some additional things here that we didn't have in the last lab. I wanted to talk about this a bit. Okay, submission requirements. Okay, maybe we didn't say this properly, so I'll say it again for you guys to hear it, right? A working link to your GitHub repo, okay, is what we're asking for. This is a lot of times the way we can check to see if, your stuff is still working to give you some kind of marks, all right, for your lab. Okay, if you don't give me this, I can't check it, and therefore, it doesn't meet submission requirements, okay? But it's not mandatory. If you don't hand it in, just lose some marks. But things that are mandatory for every lab are a completed lab report with completed features highlighted. Some people submitted their lab report, guys, and it looked empty, like you didn't do anything to it. Literally, you just handed it back to me, right? Or to Alex. You need to highlight the completed features, and it has to be something that is not just shown in the video. It has to be submitted as a separate submission item. Okay, so your completed lab video has to be something that we can see that is highlighted. If it's not highlighted going forward, you will receive a mark of 0. Just letting you know. Okay, this is a requirement. Mandatory, a short video. People did not submit a short video, but they submitted a lab report. If you don't submit a short video going forward, you'll receive a mark of 0. Okay, so please make sure you stick to the mandatory requirements. On that, please do not embed your lab report inside of a zip archive. Okay, please do not embed your video inside of a slide deck or a zip archive. Don't embed them. Make them separate, a separate link. Please don't use MP4s, okay? Use some kind of clickable link like YouTube, okay? You guys mostly live in Toronto or in Canada at this point, right? You need to submit something that is clickable. YouTube is available for everybody, all right? And if you're afraid of creating something on YouTube because of privacy issues, make it unlisted. Please do not make your video private. If you make your video private, we do not have access to it. Okay, so you need to make it unlisted. Sound must be at a good level. Video must be at a good level, a good resolution. Okay, that's what's coming up. And this is worth 8% of your final grade. So it's like a bit of an assignment, right? It's like an assignment. And it's due not this week, but the week after. We're going to go through the details of what this is this week together. And Alex will start it off. He'll start us off at the gate with a bunch of notes that he wants everyone to do. There's 2 parts. That means your lab report will also have 2 parts. Okay. Questions around labs and assignments going forward? Hopefully there's no more questions for labs and assignments. Okay, let's move on. So that is assignment 3 and 4. Assignment 3 and 4 are due. They are assignment 4 cannot be done without an assignment 3 being completed. If anything, I want to be clear on this, that assignment 4 depends on a completed assignment 3. And I'll tell you guys, this is a bit of a risk for you guys. If you're planning not to do assignment 3, assignment 4 could be undoable, which means there is a good amount of marks that you will lose. Between these two assignments, this is worth 25% of your final grade, right? So please endeavor to get both done, right? Join groups that make sense. We've given you the ability to switch groups because you can use any assignment 3 as a base for an assignment 4, which means if you and 2 other members get together and you make an assignment 3, any one of the 3 members can split off and make another group or join another group and use their assignment 3 as a foundation for an assignment 4. But not having a foundation of an assignment 3 will net you 0 marks for an assignment 4 because you must have everything that is included in assignment 3 to create assignment 4. Aiden, people do things for really weird reasons. They decide for whatever reason that they can't submit assignment 3 on time, or they don't make one, or whatever. I'm not saying that you would choose to do that. Sometimes it happens, right? I'm just pointing this out way ahead of time, before assignment 3 is due, before assignment 4 is due. I'm letting you know that this is a risk for you guys, all right, if you don't get it done. So that way you don't get upset when you come to assignment 4 and you can't do it because it's mandatory to have assignment 3 done, okay? And this is normally not the case. Like assignment 2 and assignment 1 didn't depend on each other, guys, right? Just to be clear. Assignment 2 was independent of assignment 1 and the other way around, right? So you could do assignment 1 and you get marks, and if you didn't do assignment 2, you still got the marks for assignment 1, and the other way around. You could have not done assignment 1 and decided to do assignment 2, and you could have got the marks for assignment 2 and whatever. But here it's not the case. Assignment 3 and 4 are given to you at the same time. I want you to consider this as a bigger assignment broken up into 2 parts. Okay? It's almost like assignment 3 part 1 and assignment 3 part 2. Okay, moving on. We're sitting here at week 9, and again, you can see that one half of the lab 6 is starting this week, and the other half of the lab 6 is next week. This is again prep for your assignment 3. A lot of the stuff that's happening in assignment 3 is happening right here where we build our tree node class, our condition, action, and line of sight. A lot of this stuff, which is in the first half of lab 7, is going to be stuff that's going to feed directly into assignment 3. But lab 7 depends on having a lab 6 as these things become cumulative. Let's talk about decision making. I've talked about the admin. Hopefully you guys are all good with that stuff. And we'll talk more about this stuff. I know it sounds harsh, the 0 stuff. You're going to get a 0 if you don't do this. You're going to get a 0. I don't want to talk about that. I really want to talk about what you can learn from the stuff that we're doing together. Just please, what I'd ask is do your best to adhere to the submission requirements. The submissions requirements aren't there to be oppressive. They're not like that. The submission requirements are there to be fair and to make them, marking for us, as straightforward as possible. Okay. Let's talk about decision making. So when we think about decision making, it's like the ability for an autonomous character to decide what to do. Very straightforward, right? And if you think about it, up until this point, all we've been doing is movement. Okay, and movement is not really AI. Sure, it's one part of it, knowing how to move, moving in the direction that we want to move, avoiding, collisions and those kind of things, or avoiding obstacles when we're moving. These are basic patterns that we're going to use as a foundation for everything that we're doing for assignment 3 and 4. But decision making is really the heart, if you will, of AI. How does an AI make a good decision, as an example? And the decision can be things like, I want to fire a bullet at the player, or I want to attack the player in melee combat, or I want to run away. How do you make those decisions, right? It's got to be based on some kind of conditions, all right? So that's the decision-making process that we're going to talk about, starting today. So today, in the second half of semester, it's about decision-making. So really, at the end of the day, when we think about a great game, it's going to be making an AI that is, challenging enough for the player so that the player wants to continue playing, right? And for some games, example, the latest game that we've been talking about, which is Elden Ring, right? It can be so difficult, right? So difficult that players just stop playing because it's just too much of a challenge for them. If you're a casual gamer, a Souls-like game, maybe something that you don't enjoy, right? For some people, they thrive on the challenge and they want to step up to the challenge, or they've been playing Souls-like games for so long, this is not a big thing for them. Again, things that we want to avoid, and that is another criticism for the latest game, Elden Ring, is that all the bosses that you fight follow the exact same pattern. Doesn't matter when you fight them. They have some kind of attack pattern that they use, and at the end they use kind of a one-shot kill. And basically, what you're supposed to do is avoid the one-shot kill and go in and slowly whittle the boss down until they're dead. And so they talk about that. They actually talked about that inside of any of the reviews you read. If they're really comprehensive, they go into that detail. Absolutely, Nicholas. I think that anything like that, where if it's predictable, if it's a predictable AI, or if it's something that makes, when the AI makes like really dumb decisions, right? And it keeps making that same dumb decision over and over again, you got to consider that the AI either isn't written properly, or it's run itself into a corner where it doesn't know what to do, right? So it becomes unrealistic. And when an AI agent is unrealistic to us, it breaks our immersion for the game. It stops us from suspending our disbelief. We start sitting there saying, that really sucks. That's dumb. I'm just going to, kill this creature because guess what? I can do it. And sure, I just beat it, but I didn't use I don't think I deserve to beat the game. As an example, because it just got stuck. The AI got stuck, I'm cool. And if it's an exploit, you can make it so that the AI gets stuck or falls down and kills itself or whatever. And that's something that walkthroughs go through. They go through and say, well, if you go this way, as an example, you can avoid the AI. And this character, this really big, powerful character, will fall down a well, as an example, and it'll give you the experience points that you would never get until like the end game. A good example of that is Demon Souls, I'm thinking. Where you can lead one of the more difficult, kind of sub-bosses. I don't know if you want to call it a little boss or whatever. In the beginning of the game, when you start playing the first part of the level, you can lead them so that they fall down a well, and all of a sudden you get all kinds of experience points and extra stuff that you wouldn't be able to do unless you did that. And it's an exploit. We don't want these things to be part of our games, typically, right? Unless that's how you planned your game. Yeah. So that's the kind of thing we want to talk about when it comes to decision making. Most games use 3 different kinds of decision making systems: decision trees, state machines, and behavior trees. Okay, so those are the 3 types. We're going to be talking about each of these types of decision making systems over the next 3 weeks, starting with this week. So this week is about decision trees, next week is about state machines, and the following week is about behavior trees. So we're going to cover all these things, right? Other kind of game systems use a rule-based system, and it's more rare, but it makes the AI a lot more visceral. It makes it more realistic, right? And so it increases the immersion of the player. Really hard to pull off something like this, where they can make multiple decisions based on a set of goals, or they can even express emotion or change their opinion about the player, that kind of stuff. It's rare. And the reason why it's rare is because it's hard to code. It's very, very hard to code. But we'll talk about this in a little bit more. So again, when we think about decision making, it's really the middle component of our AI model. So we've talked about movement for the first half, and then we have strategy, and then before we actually get to some strategy, we have to make some decision making. It kind of leads into from one thing to the other. And of course, the movement feeds into the animation algorithms and the physics algorithms that it's going to hit later on. Okay, so we're also going to cover tactical and strategic AI as an example at some point in the second half of the course. We'll talk about these kind of things as well. So really, when we think about this, let's just kind of really boil decision making down a little bit, right? An AI has some kind of information. The information, right, that it uses to generate some kind of action. Okay, that's what it is. We have some input, to the decision-making process, which is knowledge. And usually that knowledge is knowledge that can be broken down into two types of knowledge, right? It's external knowledge and internal knowledge, okay? And then we have that knowledge and it outputs to some kind of action request, all right? So really when we think about external knowledge, when we think about AI, we think about stuff like the position of our autonomous or other autonomous characters, the layout of the level, external knowledge, almost like game state stuff where it knows things about the game. Okay, what does it know about the game or the gameplay mechanics, if you will? If the player has been detected and potentially the player's position, those are all external state stuff, external knowledge, right? And then there's internal knowledge, things like its internal state, its health, its other statistics, whatever the stats are like. It's armor, if you have an AI that has armor or other things. Access to abilities like buffs and special attacks. Does it have those things, right? Are they available? Are they timed out? These are all interstate stuff, right? And thought processes. What about the ultimate goals? What about there's a goal? Like, for example, I made a guard that has to guard. That is the goal of the AI, to guard and prevent the player from going through to this as a gateway guardian, if you will, a threshold guardian that prevents the player to go to the next part of the level. That is their goal, right? Or maybe their goal is self-survival. They have a kind of a set of goals, and one of them is like self-preservation, right? So those things are internal knowledge. So there's external knowledge and internal knowledge, right? And typically this knowledge really drives decision making at the end of the day, right? We have some kind of internal data, and usually the state machine or decision tree, right, wants to hold, kind of what the state of the autonomous character is currently in from a game perspective, right? And a lot of times, goal-oriented behavior also needs to know what the current goal is. And my current goal might change. A good example of a current goal might be stop the player from going through the gateway, right? But then my current goal might change to be, I've taken a lot of damage, that's an internal state, self-preservation, run away from the player. We don't want to get killed here. We want to come back to fight another day. Or ring the alarm. The character has come into this thing. We're going to prevent them. The first goal might be ring the alarm. Sound the alarm because we've detected the player. We want more people to come over. That's strategic AI, right? And now let's defend the player. Let's make sure that they can't get through this thing and make sure some of the other troops that I have available are going to come out and fight the player, right? Meanwhile, I'm going to defend the player as a final boss, right? So this is all internal stuff. And a lot of times, the algorithms themselves control what internal knowledge can be used, whether it's storing goals, states, plans, probabilities, whatever you're going to do, although they don't constrain what the knowledge represents in game terms. So that means that, I'm not going to stop, a lot of times the algorithms don't stop that knowledge from coming inbound, okay? So really, the behavior of an algorithm, right, can affect the game in a couple of different ways, right? One is it requests an action, right? So that will change the external state of the autonomous character. So for example, things like they're going to fire a weapon, they're going to move into a room. Moving and firing and fighting and all those kind of things, that's external stuff. And they're also going to change the internal state, right? Which is maybe I'm going to get a new goal, or guess what? I'm going to have a different probability to do one thing or another thing. We're going to talk about probabilities in a bit, because one thing I want to mention just ahead of time is we don't want an AI to be predictable, okay, no matter how good it is. So again, we have these two inputs, internal knowledge and external knowledge. We have some kind of decision maker, that algorithm, and the algorithm is going to spit out an action request, right, as an example, which is going to, again, influence the external. It's going to, kind of create external changes and also internal changes, which is going to feed back and change the internal and external knowledge of the autonomous character to make another decision. Typically, that's how it goes. It's almost like a feedback loop, if you will. So a lot of times, internal state stuff, even for us, is less visible. We can't really read minds, right? So I can't read your mind if what you're going through when it comes to making a decision, right? We can only see the external stuff, like what the actual AI did. So which means that internal state stuff is way more difficult to troubleshoot and debug than external state stuff. I can see that the player has moved. I can see that the autonomous character has fought or run away or whatever. David's asking, would you set a series of behaviors that are chosen randomly by AI to seem different in enemy movement? Yes, that is also, we're going to talk about random stuff. And a lot of times, the more random a character is, an autonomous character, is when they're lower level. I want to say that kind of from the beginning. Imagine that they're not going to make the perfect decision every single time, right? Because if they made a perfect decision every single time, right, it's like saying, if I was game mastering, let's suppose we're playing a tabletop role-playing game like D&D, right? Imagine this scenario where I'm the game master and you're the players, right? And as a game master, I give my enemies perfect knowledge of your position. I give them perfect, responses to what you do. A lot of times, what if they have more than one player to attack? Let's say you're playing in a 5-player game, right? Which one does this one enemy attack? You, the other person, if I'm going to play in a perfect strategy game, I'm going to attack the weakest of you, right? So to wipe you out, to reduce the challenge, to the AI. But that's not realistic. Realistically, the AI may do something that is not perfect, right? As an example. And that makes it so that the game is more playable. Now, if you consider the Souls type games that are out there, so Demon Souls, Dark Souls, Bloodborne, this new one, Elden Ring, some people say that the DM that's playing, that's guiding all of the AIs is a killer DM, because he plays, a lot of times those characters do very smart things. Okay, they don't do dumb things. They're very challenging. It's almost as if you're playing against other characters, other players. That's the level of AI that they've wanted to create in those games. And it creates a very big challenge for players, enough so that it reduces the audience. And this is the risk when it comes to making games, guys. You guys are going to be making games, right? That's why you're here. And the more challenging you make the AI, that's great. But it could, and it will, reduce the audience size. It reduces it to a point where only certain people will like to play Dark Souls or Demon Souls or Bloodborne or Elden Ring. Because for other people, and there's a large amount of people like this, they find it too hard and it's not fun for them. They can't progress beyond the first part, so they just put the game away or return it. Okay, it happened for Demon Souls, it happened for Dark Souls, it happened for Bloodborne, and it's probably going to happen for Elden Ring as well. Okay, and it doesn't matter, right? I mean, there's a unique type of person who's going to play these kind of games, right? But what I'm saying to you is that it's hard to really understand or even troubleshoot the internal mental state because it's not visible. We can't see it. Okay, so that's something that we have to work on. But depending on the internal changes and depending on the decision-making algorithm, whether we use a state machine or whether we use a decision tree or a behavior tree, the end result, the external actions, could be identical. So, for example, I'm still going to do a melee attack. I'm still going to do a ranged attack. I'm still going to run away. Those are all end actions, right? Those end actions aren't going to change because of the type of algorithm. When those end actions are going to be called upon, right, or invoked, that's different. That could be different according to different algorithms that are inside of your, on the back end of your AI. All right. Let's talk about decision trees. Decision trees are the first type of, we'll say, method or algorithm we can use, to produce, decisions for your autonomous character. Okay, first type, lowest level, I would say, and they're very common still, even though not as common as they used to be. So decision trees, they're fast and simple to understand. A lot of times through this entire document, you'll see that it says decision trees are simple, simple, simple. Why? Because you're using a tree structure, and a tree structure is a data structure that you should be learning about at some point. How to make a binary tree, right? And a lot of times we want to use binary trees for decision trees because it's either I want to go left or right. I see them or I don't. Kind of a yes or no type of decision trees, right? They're very modular, which means I can add more actions, I can add more conditions, I can add more decisions, right, at the end of the day, right? And so you can start them very, very simple and move up from there. So here's the problem. So given a set of knowledge, internal and external, right, about the current state of the game and a set of possible actions, so there's two sets. Knowledge, I have some knowledge about the game. And again, this is kind of abstract, but I want you to think about things like the player position, my current position as an AI, right? This is all external stuff. do I see the player or not? External stuff, right? So that's a set of knowledge. Internal stuff, what's my health, right? What are my goals? What am I supposed to do here? Internal stuff. So getting that set of knowledge, external and internal, right, about the current state of the game that I know as an AI, right? I have a set of possible actions I can kind of take. We need to request the appropriate action. What is the best action that I'm going to use? And that's another topic of another day. What is the best action based on my knowledge? What is that knowledge that I have? And I want to create a mapping between this input and output. All right, so the input, which is my knowledge, and my output, which is the action. And sometimes that can be very complex, depending on how you create your algorithm, right? One thing is that the same action could be used for a different set of input. So depending on where I am, I might do things like, if I have line of sight, I might want to get closer to the player, right? So getting closer to the player might be an action, right? Move to the player, right? And if I don't have line of sight, I might say something like move closer to the player. I hear them, I hear the player, but I can't see the player, but I want to move closer to the player. I want to see if I can see the player, right? So move to line of sight, right? Or move closer to the player. It might be the same action, but from different inputs, okay? So we want some method that easily groups lots of inputs together under one action, right? Again, which is something that we want to do. So this is really the problem of that decision trees are trying to solve. Okay. Here's the algorithm. So decision tree is made up of connected decision points, also called choices or nodes. We're going to call them nodes, okay? And the tree has a starting decision, which is its root, okay? Whatever that starting decision is. For example, patrol. That's going to be the starting decision for assignment 3 for you guys. The patrol decision, okay? For each decision, and every time I say for each, I want you to think about a for each loop or some kind of recursive algorithm. For each decision, starting from the root, one of a set of options is chosen. Which option am I going to choose? Depending on the condition, right? These choices lead to further decisions or other choices, right? And to finally some kind of final action that I'm going to take, right? It's almost like a set of conditions, right? A heuristic in many ways, right? Of trying to figure out what to do next for the autonomous character. And each choice is made based on the autonomous character's knowledge, internal and external. Okay? So again, what we want to try and do is, we have a decision tree. Think about a tree with right and left choices. And at the bottom, we have a leaf of the tree, the bottom that has no other children. If a node doesn't have any other children, it's called a leaf node, right? Again, going back to the data structure. The leaf node, right, is the action. It doesn't have any children, right? So every part of the tree, whether it's a condition, right, that's given to us, or whether it's an action, is still a tree node. Whether it's the root node, whether it's an action, a decision, or something that's going to be a condition. It's all tree nodes. That's what they are. So we can look at it like this. So most decision trees are made very simple decisions, typically with only 2 possible responses, like a yes or a no. So here's an example. Is the enemy visible? Yes. Okay, we're here right now. Okay, cool. Is the enemy less than 10 meters away? No. Okay. Is the enemy on the flank? No. Attack. Okay, so that's interesting. So is the enemy less than 10 meters away? Well, no, but is the enemy on the flank? No, then attack. Well, how do I attack? Notice the attack is in both places, right? So it's kind of weird that this is the case, okay? Let's think about the other way. Okay, is the enemy visible? No. Is the enemy audible? No. Then what do we do? It's a kind of an end case. Well, we keep on going and loop here, right? Keep on checking if the enemy is visible or if they're audible. If they are audible, yes, then creep towards the enemy. That might be the last action you want to do. Then you're going to come back to the top of the tree again. And when you come to the top of the tree again, is the enemy visible now? Right? Oh, yes, we do see them after creeping for a bit. We saw the enemy. Yes, they are. Here they are. Okay, are they less than 10 meters away? Yes, attack. Right? If the enemy's at our flank, we don't want to attack. We want to move away. Right? Move away so we don't get attacked. Right? A very simple tree. But the problem is that we can see that attack is the same leaf action that can happen on different branches, right? Same leaf action. I'm using an attack. This is a very vague action. We want to probably call this a melee attack, and maybe this one would be also called a melee attack. Or maybe if the enemy is not flanked and you're not close enough to the enemy, maybe this will be the ranged attack type, a different type of attack, right? So again, one thing to note is that the autonomous character will choose to attack unless it can see the enemy or is flanked, right? And so that the attack action is kind of noted on two separate leaves, but it's leading to the same node, the other node, which is the attack action, okay? So let's think about this with the decision being made. You can see here that I'm going from one node to the next node. And so I go from, is the enemy visible? Yes. Right? Is the enemy within 10 meters away? Each of these questions, notice there's a question in each of these diamond nodes, if you will, that basically is a yes or no type question. A very simple true or false, right? If it's true, go to the true node. If it's false, go to the false node, right? That's really what we're doing. Okay, that's why trees are so simple to implement. And then the path for the algorithm is highlighted, the final path to the action, right? I take the move action, and then I feed myself back into is the enemy visible again? Well, I moved, right? The enemy was visible last time, right? I moved, but now is the enemy still visible? Yes. Okay. If the enemy is visible and I'm less than 10 meters away, yes, attack. But we don't care about if I'm 10 meters away and flanked, which is kind of weird, right? So again, I mean, you got to look at the tree for how it's set up. You set up the tree when it comes to behavior, and you need to check the tree to make sure that it makes sense. All right. Again, one thing to note is that the input is some kind of knowledge and the output is a single action that's taken, always. It might make a bunch of different, it might kind of go through its decision tree algorithm, but at the end, the output is always a single action every single time. Okay. So again, we want to check a single value. A lot of times we don't necessarily need Boolean logic, all right? We could use Boolean logic, but there's different data types we can use. For example, we could use a numeric value, a range of values, right? We could use a Boolean. Do I see the player? As an example, am I this range away? That kind of stuff, right? Or some kind of 3D vector, right? That has a length with a given range. And this can be used to check things like the distance between the character and the enemy, for example. So give me the distance vector. Is the distance vector less than X number of meters away? Okay. What we want to do is we combine decisions, right? And and one thing when it comes down to it is that decision trees are efficient because they're very simple, right? But we sometimes have a decision that we want to make, right? Or something, some kind of a condition that we want to check that can be very costly. Okay, one of them might be something like, what's the distance between me and the player? Now, here's something I want to ask you guys. Again, going back to that whole perfect knowledge idea and killer DM. Do you know in real life, you yourself, what the exact distance is between you and another person? Let's suppose you're in a lineup, right? Or you're in school somewhere, or you're doing something else. Maybe you're taking martial arts, and you're in a ring, and you're actually going to do a little bit of kumite. You're fighting the other person. Do you think you know the exact distance between you and your opponent? Ever? The exact distance, not an approximate, the exact distance. And I would challenge you to say you probably don't. Okay, you probably don't know the distance. So how do you know that it's close enough? We have a sense, a lot of us, especially when you become more used to fighting or those kind of things in real life. I'm talking about real life fighting, right? Then when you start thinking about what is your, kind of like your personal bubble, right? If the person's within that personal bubble, then they can be attacked. They're within reach, that kind of stuff. Where they are roughly, because you can use your sensors, your eyes and your ears and those kind of things. And if you know that they're in reach, you could perform a melee attack, right? Here's where things are different when it comes to for AI algorithms, right? They know the exact distance, right? And that a lot of times is perfect knowledge. I know the exact distance you are away from me. I think you're probably within 10 meters, right? In real life. I know you're exactly within 10 meters if I'm an AI, right? And that is a challenge. This is where we can add probability. We can say, I think they're within plus or minus 10 meters. I might guess wrong. That is a more accurate approximation of an internal state, a decision state that the AI might make. Okay, we're not going to get there today. Today we're talking about very clear-cut rules, right? Again, we're going to make one test. We have a test for each of the decision nodes, right? So the decision starts off at the top, the root node, and then we make it the next decision. Am I within line of sight? Do I have the player in line of sight? Yes or no? Yes. Okay, good. I can see the player. Good. How far are they? Are they within striking range? Yes or no? Yes. Good. Strike. That is your decision. That is your outcome. That is your action. That's a good one, David. Off by half an inch. No, I think actually what it comes down to is your experience doing something. The more experienced you are, the more reasonable you know what your reach is. But it comes down to experience. So again, going back and taking that experience, the idea of experience, and bringing it back to your AI, the more experienced your AI is, the more accurate they're going to be when it comes to firing their weapon, right, at a target towards you, right, striking you with the right types of attacks, right? They know when you're in range, defending you when you're attacking them, right, and doing all kinds of different things to foil you. Okay. So here's some example of some trees representing combinations of and or. Okay, so here's an example. If A and B, then action 1. Otherwise, action 2. Right? Here's an example of combining actions, right? If A and B. So both A and B must be true in order for me to perform action 1. Otherwise, doesn't matter if A is not true or B is not true, I'm going to perform action 2. And this idea is where Boolean logic comes into play for you guys. Where is there a way of simplifying my tree structure? Because either case, I have a default case. I'm going to do this unless these two things are true, and then I'm going to do this. Okay, so trees can represent that. Here's the other one. If A or B, then take action 1. Otherwise, take action 2. If A or B is true. If A is true, do action 1. If B is true, do action 1. However, if they're both wrong, then finally do action 2. Okay, so this is using a tree structure to use Boolean decisions. So because decisions are built into a tree, the number of decisions that need to be considered is usually a way smaller, as an example, than the number of decisions in the tree itself. Okay, the figure on the right shows a decision tree with 15 different decisions and 16 possible actions. So here's all the actions, and there's all the decisions. But guess what? Really, when we run the algorithm, we only have a small set of decisions that need to be made to run that one action, whatever that proper action is appropriately. In this complex tree structure, as an example, we have different levels, right, of decision, right? The first root node, you have two decisions, right? And then in the next level, you have up to 4 decisions. And finally, you have 8 decisions, and finally 16 outcomes. Okay. Now this is a perfectly balanced binary tree. Okay, and not all decision trees are made this way, and we can talk about them. Why is that? Because some of these decisions are going to be the same action. Some of these actions are going to be the exact same, based on a bunch of decisions. And if you have the same action at the end, again, you might consider simplifying. So we can build them in stages, and a simple tree can be implemented initially, and then as the AI is tested, we add additional decisions, adding, to trap special types of cases, right? And add new behaviors. So we started very simple. Patrol. Do we see the player? Yes, move close. That might be the first thing you want to do. Okay? And keep chasing the player. Keep moving close. How do you move? We can use the stuff we already know. We can use arrival behavior as an example. We can use seeking type behavior or pursuing type behavior. It's really up to you how you're going to move. You probably want to move in a look where you're going scenario, right? That's going back to movement, which we did in the first half. Don't forget, the moral is, don't forget what you did in the first half in the second half, because they're going to ask you to do it. Okay? Moving is something you've already learned how to do. How about branching? You have a bunch of different conditions, And here's an example. Imagine having a guard, which is an autonomous character in a military facility, right? The guard needs to make a decision based on the current alert status of the base. The alert status might be one of a set of states: green, yellow, red, or black. Black alert, right? As an example. And then using a simple binary decision-making tree described, we'd have to build the following tree. Is it black state? If it is, take the black action, whatever that is. Is it a red state? Take the red action. Is it a yellow state? Take the yellow action. If not, take the green state. So this is kind of a weird way of writing it, isn't it? This is called a deep binary decision tree because I have to have a bunch of no's in order for me to do my default state, which is the green action, right? So that's something to consider, right? And it's kind of loaded in the worst case first to kind of go something like this. Am I black? No. Is it red? No. Is it yellow? No. Okay, now we're in green. But if we're mostly in green, do I really want to check all these other states? That's the question. Do I want to reformat this tree or reconfigure, rewire, whatever you want to call it, this tree so that the green action is the default action, right? And I'm in green, as an example. I'm in green, and has something changed? Do I have an alert? If I have an alert, I'm no longer in green. I'm in one of these other ones. Which one is it? Okay. So again, one thing to note in this particular case, this is a way of doing it. Each alert state must be checked, right? The same value must be checked 3 times, right? So this is not really effective or efficient. Here's another way of doing it. We have 4 branches. Instead of having like 1 branch, again, think about this as the root. We have like really, 1, 2, 3 types of decisions to make, right? With a set of branches. Each decision only has, let's say 2 children, right? Each decision itself. And one of the children is another decision. The other child is an action, a leaf node, right? So this is kind of an unbalanced tree, if you think about it, right? Here, this is also a problem, but it's a little bit more efficient the way this looks right now, because which alert state am I in? You make 1 decision. Depending on the alert state, you're going to hit the decision that you're in, okay? Again, this is something that looks way better from a state machine perspective. State machine can kind of select one of the alert states that you're in right now and take the proper action. State machine. We're going to talk about state machines next week, okay? Again, flatter and only ever requires 1 decision, as opposed to here, I need to make 3 decisions, right? But the one thing to note is that even though the second way seems a little bit more reasonable, because there's 4 different conditions you can take, or 4 different steps, if you will, 4 connections to your root node, right? A lot of times, more often than not, we use binary decisions, right? And we use a binary set of rules, so it means only left or right, true or false, up or down, forward and back, that kind of stuff. Very, very simple. And the reason why is because decision trees, when they're in a binary tree structure, especially if they're a balanced binary tree, are very, very fast, super fast to make that decision. Okay, if they're not fast, if they're not kind of loaded that way, if they're unbalanced, we have to make many, many more decisions to get to the action that you want. Okay. So let's think about some pseudocode here as an example. We want to look at again, the tree definition. Remember what a tree looks like. A binary tree, and if we were to draw it out a little bit, like we saw before, we saw this is the binary tree, and we're looking at it kind of from the side, but we can also look at it from top down. Let's look at it for an example from a top-down perspective. So we're just going to rotate this thing right here. If we rotate this so it looks at us from a top-down perspective, and if this is the binary tree, again, we can go left or right. Right? And then if I go left, then this tree becomes a subtree, right? Again, I'm just looking at structures that we've talked about before, right? So this is the main tree, but here we have a subtree, right? This is a subtree, right? And then this subtree, when we're here at this point, this is like the new root, right? We start off at the first root, right? We have the entire tree. Now we take the left subtree. Okay, cool. Now that we're in the left subtree, now we make a decision, left or right, and now we have another subtree, right? So here's the other subtree. Now this is the root, right? This is considered the root. And now we take a look at these two, and we have another subtree that's in here. And now this is considered the root. right? And finally, we're down to two actions, action 1 or action 2, okay? That's how it works. This idea of going from a very big level here, which is the outer level, the big tree, to subtrees, if you think about what this does, it does the exact same set of algorithms over and over again, which lends itself nicely to recursion, okay? So we can call the same algorithm from within itself. Or if you don't like recursion, or if you're worried about having an infinite loop or something like a Stack Overflow, then we don't do that. We use a while loop, where with a base case, a base termination case that can stop us. A good example of the termination case in this particular scenario, if I was going to look at that, is the final case. This one basically says, okay, so when I'm here, I'm going to return the correct action all the way back to the top of the tree. So I need to get an action. That's what I'm looking for. The root is going to get one of these actions. Which action am I going to return? Well, I'm going to be here. Which action am I going to return? Which action am I going to return? Which action am I going to return? I'm going to return one of these two. Let's return this action, right? So this action gets returned back up the tree all the way out this way. And this is the output, right? And recursively, it's going to go back and return the proper action all the way to the calling state, which is the root state. Okay, that's what it's doing. It's returning an action all the way back up recursively up the tree. All right, so recursion is difficult for people to get. And it's difficult because, you know, when we look at it, it's easy to look at, but then hard to troubleshoot. And also, it's difficult to get the base case right, which is your termination case. How do I terminate it, right? So when we think about pseudocode, then we start thinking about making a couple of things, right? I want my root node, and the root node is going to have, in our case, decisions or actions. There's two types of nodes, either a decision node or an action node, okay? And the condition that I'm going to load in to make that decision is something else, some kind of condition that I want to take a look at. So I'm going to make a decision based on a condition, and then depending on that, if the test is passed on the condition that I'm looking at, I'm either going to go to the next decision that's either the true node or the false node. And if I go to the true node, again, I'm going to take that next set of, I'm going to look at the condition, the next condition that I'm going to be looking at for that particular node to make a decision whether I'm going to keep going or have an action to take. That's really how it works, okay? So again, a lot of times in object-oriented languages like C++, we could make them subclasses, right? So example, we might have a abstract superclass called decision tree node. And this is the class that all other classes in our tree derive from. Okay, this is some pseudocode. And this class, decision tree node, has a function that we list. A lot of times this function is a pure virtual. We know that it's going to return out a decision tree node. That's what it's going to return. When we make a decision, we want the decision tree node that's going to be returned back out. Why can this not be an action node? Because, well, an action node, remember, an action node is a decision tree node. It's a special form, a specialized form of decision tree node, and it's usually the leaf node in the tree. Pretty simple. All right, so actions, right, basically contain details of the action to run if the tree arrives there. So an action would be take this action, right, whatever that action is. That action is going to be something that is going to be, we're going to return back out of the tree again. That's what the decision tree is going to return, the action to take. So I'm at the top of the tree, I'm making a decision. Whatever that decision is, I'm going to return an action. And that's really my goal. My goal is to return the appropriate action to take, whatever that action is. It's going to be another function. Example, move the player. You know, move the autonomous character. Attack, right? These are all different kinds of actions. Patrol, right? Flee. All right, so making a decision then is an action, really, extends the decision tree node. So it's a subclass of decision tree node. And make decision is basically to say, okay, I'm going to return out the decision tree node. And what am I going to return in this case? I'm going to return this action. So whatever this action is called. That's why this is kind of the leaf node, the bottom part of the tree. When I say return this, I'm actually returning out the action that's linked to what needs to be done. When I come back down, then I can take that action. Whatever that action is the action that's going to be taken. Okay. So again, a little bit interesting to wrap your head around, but really what we're doing is we're just getting down to that leaf node, and that leaf node is going to inform us of which action we're going to take. Decisions, follow a different format. So actions are pretty simple. Actions of the leaf node, but decisions, right? They also are a type of decision node, right? Tree node, but they have two other decision tree nodes built into them, right? So remember when we make a binary tree, like we talked about, we have the left node and the right node. We might have the true node and the false node. These nodes refer to other nodes inside of the decision tree, and they're usually pointers to another decision tree node. One thing that's missing from this example right now in the actual tree itself, the decision tree itself, is you need a way to load or assign nodes to the tree. So all the tree itself, if you think about it, and if we were to draw it out again, and let me just use that same structure at the top, right? So imagine that I have a tree that looks like this again, right? So this is the tree, right? But each of these objects here are tree nodes, decision tree nodes, right? So when we think about it, if I'm in a decision, not an action, then the decision either has the true node, right? So this would be the true node, let's say, right? So this is true, right? And this is false, right? So if we're going to kind of, do it over here, this is the false node, right? So I'm going to be doing trues and false every single time, right? Depending on when I make a decision, either true or false, whatever this decision is. And the true node is going to be this one. The false node is going to be this one. Now we're here again, and we have the same two sets of decisions to make, right? Where we can say, well, okay, I have my true node and my false node, right? So whatever this decision is, okay? And it's going to basically be loading it on. So when I load the tree, there's one function that's missing, which is add a node, add node to the tree. Where is it going to add it? We're going to add that node on. When we build the tree, there must be some kind of build tree function that creates this tree structure, right? And we do that at the beginning. We build the tree, and that tree is the tree of knowledge, if you will, the decision tree, the tree that one AI is going to use, okay? And once we build it, that all AIs that inherit from, if we make multiple characters, autonomous characters, they'll all follow the same tree structure because all of them will have a tree that they've been loaded with, almost like a brain. The AI brain that they're gonna use, and that AI brain is gonna follow the same decision matrix that we're showing right here. Okay. Okay. So that's what the decision has these two, a true node and a false node, and then it also has some kind of function that tests the value, right? And that value is going to basically decide whether I'm going to get the next branch, right? As an example, or make a decision. If I make a decision, that's going to take me to the next node, true node or false node, depending on if the test that I've created, as an example, if the test that I've created is true or false, it's going to get me the next branch. The next branch is going to be the next decision, and the make decision is going to take that next branch, right, as an example. And again, notice that make decision is going to return a decision tree node back up the chain. Okay. All right. There's different kinds of decisions. We've been talking about true false type stuff, but you can also have a float type decision, right? So this might be a a standard decision, which is either true or false. But you could have a float type of decision which extends, the decision class itself. So again, a subclass of the decision class. And the float decision will basically take two values, a min value and a max value. And when we test whatever the test value function is, it's going to take, as an example, what if it's passed or failed, it's going to return a float. And that value, that float value, is going to be something that we're going to use in here in the get branch. Right, so get branch is basically going to say it's going to return a decision tree to go to, right? It's not going to go to a true node or a false node. It's going to decide which decision tree to go to based on, as an example, well, again, it is going to return a true node or false node, but as an example, it's going to make that decision based on if the test value, whatever that test value is, so maybe a value from the real world that's passed into this thing, as an example, falls between the max value and the min value. And depending on if it falls in between them, we're going to retrieve, kind of return a true node, the right path, let's say. Otherwise, return the left node. Okay. So that's something interesting that you might see as well. So that's a float type decision. And there's other ones you can make as well, just like this. Okay. Again, a decision tree can be referred to by its root node, the first decision it makes. And the decision tree algorithm is recursively performed by the make decision method. So again, your decision extends the decision tree node. And when you make decision, what you're really doing is you're saying, okay, so what is my branch? Well, it's going to be of type decision tree node, and we're going to get the branch that makes sense based on the value that we're testing. And what we're going to do is we're going to return whatever that branch is. Remember, the branch is the next decision in the tree, right? We're going to return its make decision function. Then if I go back down into that decision is going to make a test, and it's going to return the next branch's decision on the way out. And if the branch, the make decision function is an action, right? Going back to the action, make decision is just going to return the action back up the tree. That's what it's going to return. So finally, you're going to get all the way back up the tree because it's going to return. This is the base case where the action is the leaf node. It's going to return itself all the way back up. And when it returns itself, you can check for the type of whatever that object that it's returning. And if the type is whatever that action name is, and maybe we can have additional information in here. For example, right now our decision tree node is very simple, but it might also include a name, some kind of string array or something like that that identifies which one it is. And if I return that action, it might have a name that it returns out. And then from there, I can make a decision. I can call that particular function, right? David says, so is this generally the way a game with different levels of difficulty work? There are decision trees associated, loaded into the AI with altered variables. Again, internal and external knowledge, right? As an example, you have a decision tree. Now, this is just one algorithm. There's also another way of doing it with state machines, and a third way, which is more complex, which is behavior trees. And we haven't even talked about things like goal-oriented systems, like where an AI has a goal, to meet, or maybe they want to learn, like learning-based systems where the AI is exploring the world, and when they explore the world, they learn how to do tactics based on what they've learned. They're exploring it like you. All right, they have no knowledge of the world, and they basically explore the world through another algorithm, okay, offline a lot of times. Okay, so yeah, so there's different ways of doing it, but this is definitely one way. All right, so cool. So that's what this recursive stuff does. Make decision is called initially on the root node of the decision tree, and it decides which way to go, right? Depending on whatever that branch is, that is the thing that we're going to make the decision on. It's very straightforward, okay? A lot of times, we might have multiple branches that we want to go to, and we might have, depending on how we want to make it, we might have multiple branches, and each branch, for example, you might have a decision tree that's not balanced, and you can have something called daughter nodes, which is a mapping between possible values of the test value and the branches of the tree, right? So kind of a way of skipping across different branches as well. So really what we talked about before is we want to think about this knowledge representation. We're representing the world, right, with primitive data types, true, false, close or far. We can see them or we can't. Something very straightforward when it comes to this kind of stuff, right? So one of the benefits is we don't need a translation, right, of knowledge from the real world or the game world into the decision tree. But that's also, it's the same advantage is also a disadvantage. It's advantageous because it's quick. It's disadvantageous because a lot of times we can get into a loop. Okay, we're going to talk about that in a second. So again, we don't translate anything. We access the state of the game directly. Again, if a decision tree needs to know how far the player is from an enemy, then it will most likely access the player and enemy's position directly. All right, so again, this is not as realistic. And this lack of translation a translation can make it really difficult to find bugs because we're getting information directly from the game world, right? And again, if the decision is not very is a rarely used decision, then it might not be obvious if it's broken, and if that's the case, then we're not going to be able to fix it. Okay. A lot of times also is if something changes up the chain, we can also make it so that the game will break. A good example of that is if you have here you have a camera a security camera that is looking in a particular angle, and maybe in the beginning the implementation uses a simple Euler angle, in degrees, but later on it's going to return, let's say you've made a change to your representation and now it's returning a full quaternion, right? Which is not an angle in degrees, and then you're going to fail. You're going to keep failing the test because you're looking for an angle in degrees, but you're getting something else. It's going to always fail. Okay? And this can be something that happens that you don't really plan for, and it's not obvious and difficult to find. You're like, oh yeah, I'm asking for a quaternion now. I don't want an angle anymore. Right? Same thing. You're still looking for the same thing, where the camera is pointing, but you're asking for different things. So one of the things we got to talk about is the performance of decision trees are actually really awesome, right? They're really linear in terms of the number of nodes they're visited. The more nodes, they're going to go from one decision to the next decision to find the answer, right? And so they have something called, they usually take constant time, but there's sometimes execution time can be, can be modified by things like getting the line of sight, figuring out the distance. Anything that's computationally expensive can slow a decision tree down. And that's why we want to not do those things unless it's absolutely necessary. Okay. What we want to do a lot of times is balance the tree. So here's an example of two decision trees. There's an unbalanced tree and a balanced tree. And we can see that in the unbalanced tree, just like we saw earlier with the alarm states, we're going to go through each decision. So we're making 1, 2, 3, 4, 5, 6, 7 decisions in order for it to get to the H action, whatever that action is, right? Potentially. That's the worst case scenario, right? Whereas in a balanced tree, to get to the H action, we're only going to make 1, 2, 3 decisions. Okay, so this is the balanced tree example, right? So that's why it's good to have a balanced tree that is in binary format. Could you make a tree like this? Yes, you could. Should you? No, you shouldn't, typically. And I say typically because sometimes we have a tree that's very short that only has these 2 decisions, and it might be just simpler just to do it this way. So, so again, both have 8 behaviors and 7 decisions, but to get to the behavior H for the second tree is faster. It only takes 3 nodes. Okay. And again, a balanced tree, again, we talked about it as theoretically optimal, but sometimes that's not really realistic. As an example, because we might be trying to solve a problem when it comes to a decision, and we can't make it a balanced tree. Okay. One thing also is that all decisions are equal. So a decision that is very time-consuming to run, like we talked about before, computationally expensive, should only be taken again if it's absolutely necessary, because it can affect the performance of the tree. Let's go beyond the balanced tree. And what about doing things like pruning and like doing things like this, right? If you notice here, we have a merging of branches. Okay, so I have 2 branches as an example. I either go to this branch or this branch, but either one can take me to the same action or the same decision again. This could be similar to saying I go through from one cavern. I only have 2 paths, the left path and the right path. I choose to go through the left path because it looks nice. But then when I go back to this path here, this path can also lead me to the river, just like this path can lead me to the same river. It's just that the cavern has, it goes to the same location, okay, as an example. Sometimes this also could be, well, do I have line of sight? Yes or no, right? If I don't have line of sight, well, one of my decisions are, if I'm really, close, move towards the player. If I don't have line of sight, I can say, well, if I'm really close, move towards the player, right? So this might be a movement action, as an example. So I'm using one action that is the exact same for both nodes. So this is kind of like a bridge, if you will, or merging of the 2 branches. Okay, and it doesn't just happen once; it happens again. So this is the first merge, right? And this is the second one, where you can see that these two paths from this one or this one lead to the same thing, okay? And what this does is it reduces the number of output actions at the end of the day, right? That's what it does. So instead of having, you know, a tree that has 8 actions, you know, here at the end, let's suppose it has 8 or more actions. Now it only has 6. Yeah, because these are only the actions that we can take. So so that's more realistic. A lot of times we kind of load the tree. When we build our tree, we build it manually. A lot of times there's no automatic building of the tree. We build it, right? And when we build it, we might decide that, you know, 2 actions lead to the same node. But be careful. So a lot of times what I like to do is draw it out. Draw out your tree before you make it so that you understand what you're building, what decisions you're making. Okay. The other thing that we want to think about is our code supports loops, right? So example would be something like, well, I'm not close. So what am I going to do? If I'm not close, well, then go back to the previous thing and keep doing this. This is also supported. So be careful not to do this, like where you recurse back to the previous tree. And if we're not close, then it's going to keep on looping forever. This is something called the pathological tree, where we can actually loop forever, right, inside this thing, never finding a leaf. Okay, this is also a bad thing. And this can happen with pathfinding as well, where there's no place to go. Keep looking. Look for the shortest path. There's no shortest path. Keep looking for the shortest path, as an example. Because, by the way, you can use binary trees for, you know, looking for the shortest path. We talked about that earlier this semester. One thing that was mentioned earlier is, what about randomization, right? And I think one of you guys brought it up. You said, like, you know, can we make it so that it is, David said, you know, would you set a series of behaviors that are chosen randomly, right? And that makes it more realistic because we don't want an AI to be deterministic or predictable, right? We wanted some random choices to make it unpredictable. But I have to say that making random choices makes your algorithm difficult to test. And why? Because let's look at this one. Imagine running the following tree every frame, okay? Where if I run it every frame, this can produce a lot of jitter, right? So am I under attack? Yes, defend. Okay, next frame, am I under attack? No. You know, what do I want to do? Do I want to patrol or stand still? Oh, well, now I want to randomly heads, I patrol. Next frame, I come back. Am I under attack? No. The next frame, I flip a coin, I'm standing still. So you can look at, like, the player, the autonomous character can be looking like they're patrolling and then standing still, patrolling and then standing still, and over again. This is terrible, right? So be careful about this loop that can happen. It's very common and easy to fix. And the way to fix that is to make the random choices stable. So if the world hasn't changed, stay doing that. Continue doing that action if the world hasn't changed, right? If the world changes, then make that random decision again. Okay. One thing also to do is to keep track of what was made last time. So let's say you're doing random decisions for a length of time, right? As an example, then what you want to do is you want to keep track of the last decision. So the next decision you make won't be that last one. It'll be something else. Okay. And again, if you had a set of 3 or 4 decisions to make, keep track of the last one you did and choose from the other 3. Okay. To make it more random. And you can see that what a random decision in pseudocode would look like. It would look something looks like this. It would say, hey, here's my random decision. It extends a regular decision. That's what it does. And we can take a look at the last frame, right, which is an integer, -1. And then what is my current decision, right? Well, it's going to return a type of Boolean, which we initialize everything as false. And then we have our test value, which returns a Boolean. And we say, well, if the frame is equal to the current frame, whatever that current frame is, and if my frame is greater than the last frame plus 1, then the current decision is a random Boolean decision. Otherwise, if it's not, then the last frame is equal to this frame, and then, you know, keep doing what you're doing. And one thing that we also want to be able to do is timing out. You know, if an agent continues to do the same thing forever, like keep patrolling forever, it kind of looks strange. If you're watching an AI, so maybe make it do idling for a while. Maybe it idles for a while, it looks around, and then after a random interval, it starts patrolling again. Right? That makes it more natural and less deterministic. It also makes it more difficult for the player to predict, right? Which is not what we want. We don't want a predictable AI. Even if the predictable AI, think about it this way. I fire a bullet at the AI is going to hide behind a block. Every single time I fire a bullet at the AI. So it's going to fire behind a block. So if I know I'm going to fire a bullet, I'm going to prepare for it to go behind the block, and I'm going to go there, right? So it's predictable. I don't want that to happen. Maybe when I fire at the bullet, sometimes it fires back, right? That's random decision tree. A lot of times we can modify the random decision that we make with a timeout, so that after a certain amount of time, it stops doing that thing. Maybe the timeout is something like every second it does something different, or every 2 seconds, or whatever it's going to be. Every X number of frames. All right, so that is decision trees in a nutshell, guys. It's a very high level overview of what a decision tree is. At the root case, remember that a decision tree is just a binary tree in most cases. Okay, a binary tree with left and right choices with children, right? I have my root node and I have a right node and a left node. That's what I have, okay? So that is a binary decision tree, left node and a right node. Questions around decision trees before we stop the lecture piece? Okay, before I go into the lab, and I'm going to run just a little bit over time today, I'm just going to talk about the assignment 3 really briefly, because I think it's worth talking about again, okay? And now that you know a little bit more, we've talked about decision trees, right? Let's talk about that assignment 3 again. So again, one thing to note is assignment 3 is due March 27th. So again, a few weeks away. And you may work alone or with a partner for a total group size of up to 3 members. Okay, so again, up to 3 people. Mandatory criteria are marked as mandatory. A start scene, you guys have done all this correctly, so hopefully you won't have a problem with this. That's not going to change much. The play scene is where things change. You're going to include a node class as discussed in our class. You must create a collection of node pointers to enable iteration across all nodes. This could be an STL vector. And we're going to do that this week when we create a grid of nodes. All right. Ensure you select an appropriate actor sprite, again, like before, and create an interesting map. All right. Again, overlaid on top of the nodes. So they're not tiles, right? They're nodes now, which is a little different. Your play scene must include appropriate background music, and you must have some sound effects. So this is kind of a setup like we had before. And we talked about there are set up all key elements that will be reused in assignment 4. These include line of sight, detection radius, player movement, enemy movement, and a bunch of others, right? You have debug keys we talked about before, different kinds of animations and sounds, and player combat capabilities. All right, the player has a close combat, should be able to do a close combat and a ranged combat attack. So that's something you can start setting up now, guys. You don't have to wait for me to show you how to do a close combat attack with the player and a proper animation and sound effect. Do it now. Get together with your teams and start working on this right now, okay? Health bar is, again, something you can work out on your own. You don't have to wait for me to tell you how to do stuff, because you know how to do a health bar at this point. Game status, some kind of progress bar. Health bar or progress bar is very similar. Obstacles, you guys know how to put obstacles in. And this is where things get a little interesting. The base enemy class, where the base enemy class can do a patrol action. That's what they can do, a patrol action, okay? So again, that's really it. Base enemy also has a line of sight. We're going to show you how to do line of sight, as well as a detection radius. All right, detection radius and line of sight, you need to have these working, because if you don't have line of sight and detection radius, you won't be able to do assignment 4 properly. Because those are the 2 conditions, if you will, that we can test to see if the enemy is going to do something different. Okay, that's it for assignment 3. For the most part, you can get going on this right away, and you don't have to wait to get this going. All right, so please start assignment 3 as soon as possible. All right, so things that we're going to cover this week in our Lab 6 goal is we're going to clean up the play scene together. We're going to review line of sight, because it's part of your assignment 3 and 4. We're going to do line and line rect type intersection test to kind of create that. We're also going to create a path node class, which replaces our tile class, as well as we're going to create a grid of path nodes that we're going to also have. And in IMGUI, so IMGUI is going to be used to will be used to show and hide the path nodes. And usually the path nodes are going to be kind of like this blue square, okay, that's going to be representative of our path node, a little blue square that's going to be in all across the screen, okay? So why is that? Because we're not going to worry so much about, one direction anymore when it comes to movement. We're going to use a different way of moving, not A-star pathfinding, but rather we're going to be using line of sight, okay? So a lot of times what we want to do is gather line of sight between two nodes. So again, example, if I was going to create on the whiteboard a set of nodes, let's suppose this is your screen really quickly, right? Here's your screen. And I have a bunch of these nodes. Let's make these nodes a little bluer. There we go, blue nodes. And let's suppose I have a blue node here, and that's what they're going to look like, a bunch of nodes all over the screen. Let's suppose I have some nodes over there. There'll be more nodes than this, okay? There'll be nodes all over the place, right? Then what I want to do is I want to detect line of sight, right, as an example, between this node and this node, and between this node and this node. Do I have line of sight between these two things? If I have line of sight, then I know that there's no obstacle, right? Maybe the obstacle that we're going to have in our way, in our map, is going to be something that looks like this. So there's line of sight with these ones. But what about these nodes, right? What about if I go back, to another node, these nodes right here? This node here has no line of sight, right? Because line of sight would stop, right? If it would stop to here. So it would kind of, from this node, if I was going to try and draw a line to this one, we clearly see that this has no line of sight, right? So this would be a great place for a AI to hide, right? If I want to pop behind an obstacle, to hide behind an obstacle, we need to know if there's line of sight between these nodes, and we're going to do this next week. For this week, we're going to set up the nodes again in our lab to kind of showcase that we can actually know, kind of set up a set of nodes all over the screen, and then we can put obstacles in the way. And if there's an obstacle from one node to the other, we won't have line of sight. Very, very simple start, and a different way of navigating the entire kind of scene without using pathfinding. We'll be using it, we'll use line of sight in order for us to move things around, as well as sensing radius. And sensing radius will be a radius that kind of goes outside of the particular enemy. Let's say, for example, the enemy, like we said before, is, let's make it black. Maybe the enemy is right here, right? And they have some kind of sensing radius. This is the sensing radius. If the player can be detected in two ways, I can see the player, and let's say the player is over here, or I can detect the player, they're in my radius. Those are the two things we're going to be looking for in this assignment. Okay, so that is the stuff that we're going to be looking for this lab. And that's really it for me today. Any questions around decision-making, assignment 3 that's coming up, or anything else we've talked about so far today? Assignment 3 starts building on Lab 6. Absolutely, because Lab 6 is something that we're going to do. So we're going to wipe away the stuff that we already have, the tile, the grid, the pathfinding, all that stuff. We're going to get rid of all those things again, and we're going to start fresh with a whole new set of things that we're going to ask you to do. Okay? But each lab builds on the other lab. So Lab 6, Lab 7 will build on Lab 6. Lab 8 will build on Lab 7, and so on until we get to the end. All right, guys, thank you so much. Good luck. And again, if you've submitted assignment 2 and you get a 0, again, there'll be cases where we're going to go in. Alex and I are going to be adjusting things and giving you a chance to get part marks if you're one of these people who just has a broken video or something like that. Okay, so hang tight. We're going to get to that in a bit. And for anyone else, I'm going to hang back. I'm going to stop recording now. And for those people who have any questions, I'll be able to try and answer some of those questions for you. Otherwise, for those people who don't have questions, thank you so much, and I'll see you on Thursday. Take care. So let me stop recording now, and we'll get to the next piece.